Okay, so we're going to talk about landslides today. So the technical term in geology that you'll see sometimes in the articles that you're looking at is mass wasting, and that's just a general term that describes any type of downslope movement of material. And landslide's kind of the same thing. It's kind of a general term that describes kind of the same thing, but mass wasting, I guess, is the more geologic term. So that's what we're going to look at this or today. So we're going to kind of go through some of the ways to categorize some of these events because, of course, whenever we can, we want to put things in groups and so that we can look at their causes and how to fix them, right? So every group might have a different cause and then it would have a different way that we could mitigate that problem. So the first one we want to look at is what is a landslide, or like we said in our geologic terms, mass wasting. And so that's just downslope movement. So some of the terms you might hear besides just rock and soil is a term called regolith. It's another geologic term, but it's just describing any loose material. So we can have the movement of big slabs of rock that are pretty coherent, but then there's also just the rubble kind of that sits on top. That's the regolith, and it's just a very general term that describes any of that material that sits on top. So if that stuff's moving down slope, we would consider that a mass wasting event. All mass wasting events are driven by gravity. And so it's a movement process, but it's usually distinct from the typical erosion that we talked about way back when we talked about sedimentary rocks. So a lot of times weathering, which is the process of wearing down the rock, so that can be chemical or mechanical. It's breaking down the rock into smaller pieces, and then a mass wasting event can occur. And a lot of times when we talk about the scenery, like something in the Grand Canyon, or especially places in northern Arizona, that kind of scenic view is really due to mass wasting events. So, for example, on the Colorado River, it's carving the canyon down, but mass wasting, the failure of the cliffs as the river cuts down, is really what's making it wide and opening up the canyon and giving its distinct look. So that's kind of the definition of a mass wasting event. And so we kind of want to always hold in the back of our mind that gravity is the controlling force, right? This is a force that's pulling the material down. So as long as there's some type of elevation change, you will have a mass wasting event. So conversely, if you live in the flattest place on Earth, you really are not going to have any mass wasting events because you need some type of slope. But there are factors that control whether you will have a mass wasting event and what type you'll have. And so we want to look at those really quick. And so water is one of the biggest factors that determines whether you'll have some event, right? So the water does a couple things. So it actually adds weight to the slope because we know that if you carry around a jug of water, it's pretty heavy. And the other thing is that for loose material, the water is getting in between the particles and it actually reduces the friction. So if you have some type of material that's piled up and it's dry, the little pieces are actually in contact with each other and there's some frictional force there that's resisting motion. But if we add some water, it kind of acts like a lubricant and it reduces that friction. So those pieces can slide a little easier. So with the addition of the weight and some water, we can cause the material to move. And so rainfall, heavy rainfall, is one of the big triggers for mass wasting events like that. And this is kind of one of the reasons, the added weight and the reduction in internal friction. Another factor that influences whether you'll have an event is the steepness of a slope. And so the steeper the slope, typically, the more unstable that is. And so that can be from natural causes. So a lot of times, if we look at, let's say, the California coast, it has steeper cliffs near the beach a lot of times, and the waves are crashing against the bottom of the cliff, and they're removing material, and that causes the angle to steepen, and then that cliff becomes unstable, and a lot of times you can get a collapse event that way. And sometimes that's human derived. We build roadways or cut into mountains to build structures or houses, and when we do that, we modify the slope. And if we make it too steep without any support, then we can have a failure event from that cause, right? Let's see. Another factor that we want to kind of consider is vegetation. And so vegetation typically adds stability. And so depending on the type of material you'll have a variety of vegetation, but usually it's holding the soil and some of the loose material in place because the roots of the trees or plants or grass are actually supporting that. And so a lot of times after wildfires, so California is notorious for this, they'll have wildfires which will basically decimate all the vegetation. And then of course, months later, they'll get the rainy season, and without that vegetation there, then their second hazard that comes along after the fires are these big mudslides that they get, because the material doesn't have those plants to kind of give it the support. So vegetation is a big deal when we look at slope stability. We also, of course, can't forget geology. This is a geology class, so you want to look at the type of material that's available on a slope. So there's certain material that has some strength to it. So if you look at the Grand Canyon as an example, sometimes you'll see really steep cliffs there, and sometimes you'll see kind of more gentle cliffs. And a lot of that is dictated by the rock strength. So usually sandstones and limestones are very strong and resistant to weathering, and they form steep cliffs. And muds and siltstones are weaker, weather easier, so they fail more often, and they tend to form slopes. So that's one factor that geology can give to slope stability. The other is the angle of the bedding. And so we know, because we studied earthquakes, that layering of rock is usually horizontal, but when there's earthquakes, we can tilt those rock layers. And if the rock layers are actually tilted the same way that the slope is, it can allow for them to slip and slide along their bedding. And so in this little image here, you can see that the rocks are actually tilted, and on the right side, the rocks are tilted the same way that the slope is. And this is actually a diagram from a failure that happened, I believe this was in Italy, where the beds were sliding where they contacted each other because there was a weakness there. So there was a lot of rainfall, and it just slid along that contact, and they slid into the valley here. Where you can see on the other side of the slope where the actual dip of the beds is the opposite direction. It's almost perpendicular to the slope. That slope would be much more stable just based on the geology. So we want to definitely look at the geology when we're assessing slope stability. And then here's that term I talked about, regolith. So this is just almost think about the amount of soil or rock that's sitting on the hard bedrock. So this comes into play more for places that are a little more humid. So probably like the east coast of the U.S. would have more regolith, right? A thicker amount of soil or sediment because it's more humid back there and their erosion and weathering rates are a lot higher. So they'll develop a thicker soil. The more soil that's there, the more material you can move. Out here in Arizona where it's really dry, we typically don't have thick soils. And so it's not as an important a factor when we consider slope stability as it is, like we said, back east where they would have much more thick regolith. And then finally, we'll just kind of look at weight. And weight can be a bunch of things. It can be water. We already talked about that. But a lot of times weight comes from actually human-derived building structures and homes. And so, you see a beautiful view on a cliff and you want to build your home on top of that cliff. Well, when you do that, of course, you add weight to that structure or that hill, which can then cause it to fail. So we have to assess the slope when we're adding weight, structures, and things like that. So when you look at slope stability, you want to evaluate all those factors and then figure out, is that slope safe? We want to build there, or if there's a hazard there, can we fix it? And then when we get hazards that were defined as a landslide or a mass wasting event, this is where we try to kind of categorize them. It's really kind of difficult because one type of material can transition into another. So you could have a bunch of rock that falls from a cliff. But then on the way down, it mixes with other material and it turns from, a rock fall into a mud slide, so it can be kind of challenging sometimes. For this class, we just want to look at the basics. And so for us, what we want to do in order to name a type of mass wasting event is we want to either determine, is it soil or loose material like regolith, or is it bedrock? Like, did a big slab of rock fall or slide down the slope? And we would say, oh, that was rock that failed. Or was it material like soils or just the loose kind of pebbly stuff that was on top? We want to say, hey, that was debris or soil or mud or things like that. And then we want to look at how did it fall or move. And so some of the basic terms we might use for that is there are just what are called falls, and usually it's associated with very steep slopes. And so you can get rock falls, where a big, huge slab of rock just kind of falls almost straight down. And so we'd look at the type of material. It was mostly a rock or a slab of rock, and it fell pretty much straight down. We call it a rock fall. But then we can look at other ways that material can move, and it can slide. So in that little diagram I showed you, we were talking about the angle of the bedding for geology. We said that if it's tilted like that, it can move along the contact between the two layers there. So that would be a sliding surface. So if we were trying to evaluate that type of event, we would look for that feature, a surface that looked like the material slid down. So we might have a rock slide, where instead of it, free falling down, it's actually moving along a contact surface. So we try to evaluate that to see if we could discover that. And if we could, we might change our mind and say, oh, that wasn't a rock fall, it was a rock slide. And then flow is usually when we start to add some type of moisture. So we get water or something like that, and so it turns more into a flow. And so this term we sometimes use like debris flow. So let's say it's a bunch of material, big and small, it's a mess of stuff, we might say it's a debris flow. If it's mostly really fine grain, a lot of fluid, and it's really muddy, we might call it a mud flow. Maybe it's a mud slide, right? So we can kind of use these terms to kind of figure out the best way to label it. Like I said, sometimes that's challenging, and sometimes there's, and people who do this for a living, there's lots of other terms. We don't want to get too specific. So for this class, if we can figure out if it's a kind of soil, mud, debris, or rock, and then figure out how it moved, then we can try to name it. And then each of these has a different rate of movement, and so we're just going to kind of name the two end members of movement of material. So the fastest is what's called a rock avalanche, which is fairly rare. And the reason it's given this unique name is because it's usually when rocks, so these big slabs, fall great distances down steep slopes. And the fact that the mass of material moves so fast, when it impacts the ground, it actually creates a cushion of air that supports it and reduces the friction without any water. And these things move down slope at hundreds of miles an hour, and because they have that velocity, they can travel great distances. Now, this is something that typically happens in really high mountainous areas, and usually without any water, and so that's how people identify them as rock avalanches. And then we get something called creep, which is the exact opposite, something that happens super slow, almost imperceptible. So sometimes that's due to the type of material. A lot of times it's due to the steepness of the slope. So if it's not very steep, we're not going to get a lot of acceleration. So things slowly inch down slope. Maybe it might even be a couple inches a year. But given enough time, it can do some damage. And we have some keys to kind of pick up, and identify creep. And I'll show you some pictures of that. And so if we're looking at some, just some imagery to get an idea of these different types of falls and naming these features, you can see a lot of times where you have these steep slopes, you have this slope of material, sometimes called a talus slope. But a lot of this is multiple events that have occurred over long periods of time. And these would be probably mostly just rock falls. And they might be big and small, but they accumulate this massive material at the base of the cliff there. In other cases, we get stuff like this, where we would look at some of this material and say, you know, I don't see big rocks here. It looks a lot like soil or regolith, debris, maybe mud. And so we might call these, you know, mud flows or debris flows or something like that. And then let's see. So when we put all this stuff together, here's a few of the terms that we'll kind of see in this class. So we're trying to look at the type of material and the type of motion as best we can determine that. And so we can look at, you can see the names there, you know, rockfall, rock slide. We mentioned the rock avalanche. We mentioned mud flow, debris flow. Slump and earth flow, same thing. They're sometimes hard to pick up the difference between like an earth flow and a mud flow, but we can do our best to kind of figure that out. And we talked about creep as being one of the slower moving mass wasting events. All right, so let's see what else I got for you. So let's just run through a couple and I give you some images in case you're a little confused about how to identify some of these. So, you know, rockfall is pretty straightforward. It might look something like this, where it's large slabs of bedrock that are moving down slope. As straight as you can. Obviously they're going to impact and break into small pieces, but usually no water involved and things like that. And so a lot of times they'll leave a big scar like you see here on the left. And so that's one way to tell there has been an event, because of course we'll have a large slab of rock peel away here, impact the ground, shatter, and move down slope at a relatively fast speed. And of course that's going to take out any vegetation in the area, and so it'll leave a big scar there and it'll help us identify it, let's say if we hadn't seen the event. And then the rock slide is where we would look for a particular sliding surface. And in this little diagram you can see the tilted layers here. Each of these layers represents a different rock type, and we would argue that where the different colors are is what's called a bedding plane, and that usually can be a weakness where those two rocks are in contact with each other. A lot of times water gets in there and it can loosen up that contact. What we talk about water doing, it reduces friction and it allows the rock to slide on a specific surface that I can identify. So we call that a rock slide, and it can slide for a variety of reasons. The most common would be the bedding here where we have layers, but it can be from fractures or joints, or in some unique cases certain rocks like metamorphic rocks have a weird texture that are kind of linear like bedding planes. It can slide along, but any sliding surface that you can identify in the field, we would, you know, look at pictures and pick it out. We would definitely want to put that into a slide category. And so this is I showed you that picture when we were just talking about geology affecting slope stability, but this was that example where we had just an event like that where the material slid on a specifically defined surface. And so they were able to determine this was a rock slide event and see the surface that it slid on and see the material as it moved down slope here. And then the rock avalanche was the one we talked about where it can be the most kind of devastating because it's distance that it can travel and the speed at which it travels. And you can see, of course, unfortunately there's some, you know, events in the record that are kind of deadly that we can point to, and here's one where there's a town here in the valley. There was an earthquake that triggered a large massive rockfall up in the mountains here, and this rock avalanche moved down the canyon wall super fast and came out into this valley here and kind of took out that whole town. The other one that we haven't really looked at too closely is called a slump, so I'll show that to you here. So it's kind of like an earth flow where you have usually some type of mud or sediment that's moving. And so the same thing here, you know, this is what geologists do. They would go out in the field and they would try to look at it and determine how it failed. The big thing here is a lot of times you see these little scarps that develop. They almost look like a fault happened where there was some movement, but there's a little curvature to the surface that slips here. So you get this scarp, you get this little toe of material that oozes out here, and you have this, what they're going to call like a rotational surface. And if you can identify those things, then we would say, yes, that's a slump. Now, if you looked at that in the field, or we're looking at pictures, and you're like, yeah, it looks kind of like an earth flow or debris flow. For us in this class, you know, that's probably close enough. But if you look here at this image, so here's a real life image, the things that are kind of giving this away are those scarps that you see that the arrows are pointing to. So this block kind of slipped down and rotated a little bit. And although I can't see the rotational surface, I can see that the material is actually not flat anymore. It's kind of rotated. And so that would be an indication that this would be a slump. Or we could look at something like this. This one's been weathered a little more, so some time has gone by here, but it's a similar feature. And then let's see, if we wanted to look at some debris flows or mud flows, they would look something like this image here, and this is where we're introducing lots of moisture here. So they'll travel farther because they have some moisture and they're more fluid. They can be lots of small pieces, like a mud flow, or they can be debris flows where they're carrying a little bit of everything, big boulders and things like that. We did look at a little bit of this when we talked about volcanoes, right? A lahar is a mud flow that is coming from a volcano, and that's a specific type of mass wasting event. And usually there's water involved in that, and it's just taking the loose cinders and material from volcanoes. And so it's definitely associated with a volcanic activity. But obviously, like in California, we said you strip off all that vegetation from fires, and that soil is just hanging in there waiting for some moisture. And then when we get rainfall, we get these mud flows like that. And then I talked about the earth flow. You know, you could see a little bit how it's hard sometimes to differentiate this from maybe an earth flow or a mud flow, and that's okay. But it is a term that's brought up, and usually, like we said, a thick soil here, usually it's not moving very fast, and so it's not a one-time event. It's a slow kind of movement that you can see. Some other examples of earth flows like this. And then the creep is the one we talked about being the super slow one. And so usually the way you pick that out is something on the surface is slowly rotating or tilting. And this might be an indication that the ground is actually slowly creeping along. Usually you need some type of soil to do that. It's harder to have the bedrock do that, but you can see in this image here that some of the bedding is actually tilted. But we might see something like this. You might have seen trees that are curved here, and the reason they are is because the soil is actually creeping down slope, and the trees are being pulled down slope, and they're trying to grow straight up so they can get the most sunlight, and you kind of get these bent over trees, an indicator that creep is occurring. Or even something like this, where you put up a fence on a slope. It was pretty straight when you put it up, and now it's slowly being pulled over, and that's because the soil is slowly moving down slope, or you just did a horrible job of putting the fence in, either way. But this is that really slow mass wasting event. So what we want to do as geologists is evaluate slopes. And so one of the things you're tasked with as geologists is a lot of times people want to build in some area, and so the geologists will go out and assess the slope stability. And so they'll make maps and they'll look at certain factors to determine if you can build in this area. And so you can kind of look at some of the features here. And so this little diagram to the right is showing a very simplified version of part of the slope that's what we call the driving mass, which is material that's being pulled down by gravity. And then at the base here, there's a part called the resisting mass. Now, it's not just the mass itself, right? It's friction, and it's some other factors, the steepness of the slope. And so we want to evaluate some of these factors and see what's happening here. The idea is, of course, if you have more driving mass or driving forces, things that are wanting to pull the slope down, and less resisting masses, then that slope would be determined to be unstable. But if we have a lot of resisting masses and forces and not a lot of driving, then we have a lot of material and forces holding the hill up, and we might say that this slope is very stable and you could build on there. But any modification to those, which sometimes humans do, can tip it in one way or the other. So unfortunately, a lot of times we remove material from the base of the slope because we want to build a road there. Well, that's taking away some of these resisting masses and forces. Or we pile stuff on the top. We talked about weight being a factor, right? So that can cause slope instability. So we want to be able to look at those two kind of things and compare them, and that can give me an idea if things are stable or not. So on a really basic kind of idea. It's just when we take the masses and forces and we compare them, we can come up with what's called a factor of safety. And really what that is like we said, comparing them. So resisting forces divided by the driving forces. So if you have a big number up top, then you're going to have a larger number. So a number greater than 1 is stable. But if you have a very small number up top and a big number at the bottom, you're going to get a number that's less than 1, and that would be determined to be unstable. So just kind of very basically how we would calculate slope stability in the field, but you're taking a lot of data there, right? You know, you're taking in slope and the length of the area that's sliding, and you're looking at angles and things like that. So it can be pretty complicated. And so you can get into some math here and you're doing angles and all that kind of stuff. But as a general rule, we're just going to say we're comparing these overall forces against each other to see if something is stable or not. And so we talked about one of the ways that we can reduce the hazards here, right? So we also want to be able to protect people is to make hazard maps, which we do for lots of things. We make flood hazard maps and earthquake hazard maps and we make landslide hazard maps. And so geologists go out into the field and look for one old mass wasting event, something that might have occurred in the past. Can we identify that? We look at slope, steepness, you look at geology, you look at vegetation, right, types of material, and you take all those things in consideration and you try to find where the most stable places are, where the unstable places are, and it can determine whether you can build in different areas or if the area has to be modified so that it can be built. So some of the things we can do to make slopes more stable is really to look at all the factors that we talked about at the very beginning of the PowerPoint and say, how can we change those factors in our favor? And so one of the big things is get water off the slope, because we know water is a big factor for causing slope failure. So in this instance here, in order to make this slope stable, you can see there's a pretty massive undertaking, but they put in these big shafts in the slope, and then these horizontal drain pipes, so that when it rained, the rain went down these shafts into the pipes and pulled the water off. We want to lower the water table here and any water that's in the slope, because we want to reduce the weight and we want to get rid of that water in between the grains that we talked about that reduces friction. So we can do that with wells, with drains, anything like that. In some cases it can be really simple. You might have seen this little concrete thing sometimes driving on the freeway in Arizona. You'll look over and see that, and really it is a way to get water off the slope. Now, it's not covering the entire slope, but when water hits the top of this slope up here, it's kind of funneled into this little culvert, and then the water can rush down the side there, and that means less water sinks into the ground, and it's a way to get some of the water off the slope and make it more stable. In other cases, we can actually put some material on the surface that's impermeable. If you remember that term from our groundwater, where the water can't penetrate, and so it's another way to keep water from being soaked into the ground, and that way it'll just flow off, and then we can control the amount of water entering the sediment or soil. The other thing we can do, so that was kind of our water control. We said that slope steepness is a factor. Well, let's change it. So we can change it by just cut and fill. So if it's practical, you can take a steep slope and make it flat. So we cut off some of the top, we add it to the bottom, we've reduced the slope angle, and we've made it more stable. Other times we do some type of benching if it's not practical to remove all of the material on a slope. Right? You can just cut it back a little bit. The benching reduces the slope angle and then has a place for debris to kind of collect before it hits the bottom there. And that can be done in a couple ways, but it's really just to reduce the slope. We can add some support to slopes. So this example here is more for small slopes and failures where we could build some type of retaining wall or cement wall. So sometimes you see structures like this. It's basically holding back the soil here. Not going to last forever because over time that wall probably fail, but for a short-term solution it'll work. So retaining devices like that, or sometimes what we'll see is a stack of these little caged rocks here called gabions. It's really just building a wall like we saw in the previous image, except because this is just filled with rocks, water can penetrate through there. That's a good thing, right? If water gets in our slope, we want it to be flow out the front of our wall so we can get water out of the slope. So it's kind of doing us two kind of things. It's giving support, and it's also allowing water to get out that way. Let's see, what other ways? So up as you drive up Flagstaff, going up toward through Black Canyon City, you sometimes see this wire mesh fencing here, some type of support that's holding some debris onto the cliff so it doesn't come down onto the roadway. Or even there's places where we spray some type of concrete onto the surface there. And here they're doing that on the left, and on the right they're adding some reinforced, some rebar, spraying some concrete, so it's just giving it some strength. It's adhering to the rock itself, and that can reduce weathering and hold some of the material together. More we have. So when they were working on the bridge for the overpass for the Hoover Dam, they were running into some rock that was highly fractured, and so one way that they held the rock together was with what are called rock bolts. They drilled in through the layers, through the fractures, and they basically bolted all the pieces together. And in certain situations where you have that condition, rock bolts can be a way to kind of secure and hold those things together. So these are ways that we can kind of manipulate the slope to give it some strength. And like I said, mostly it's by looking at those factors, trying to figure ways we can reduce some of the factors so that the slopes are more stable. And then the last thing we'll talk about really fast toward the end is some triggering events. And so usually there's a handful of things, and some we've already talked about, but certainly some type of shock. And of course the biggest one is an earthquake, but you can get it from explosions and things like that. Even something as crazy as, you know, a big truck moving by, if a slope is right on the edge of becoming unstable, any type of shock can trigger the failure. And so we certainly have examples of where earthquakes have caused landslide events. So we know that some hazards trigger other hazards. When we talked about the Alaskan Earthquake in 1964, we know that there was a lot of soil failures there, and so that triggered the movement of the soil. Those were technically mass wasting events that occurred right near the coast there as the material moved down slope, and that was triggered by the earthquake that happened in 1964 in Alaska. And there's some images from that. Of course, if you have homes on that material and it starts moving, right, your home's not going to be happy. And then there's another example of when we talked about a rock avalanche. You know, that event that I showed you was triggered by an earthquake. And so here's another viewpoint of that. And you can see how far this material moved down slope here. But there was a large earthquake that basically allowed a big rockfall to occur high up in the mountains. But that was enough material, and it's steep enough that all that material moved down the valley and then opened up on a little town there. And so these triggering events can be very devastating because you have an earthquake, which is already causing damage, and then you have a secondary hazard, which are these landslide events that occur. And then we talked about water being a big one, and we know that water is one of the bigger triggers because it's adding weight, reducing internal friction. So places that get heavy rainfall, and that occurs a lot, like monsoon season, places in India get this, where seasonally they have just tons of landslide events because lots of water rain is falling, and that they get so much that the soil can't hold it, right? And so you get a lot of failures from just excessive rainfall. This can be caused by other factors too, but there was this example here in Italy that I've mentioned a couple times. This was this idea that the geology was playing against it here, but the trigger was the rainfall. And so the geology allowed to move along that sliding surface, remember, between the contact of the two layers. But the trigger was heavy rainfall that occurred, you know, for like a month and just soaked that material and allowed that surface to slide because so much water was penetrating down to the contact between those two beds. And so we know that that was a big hazard there. And of course, this material came down and cascaded into a reservoir, which caused a small tsunami. So this is that whole idea that, you know, one hazard can trigger another. And this is just another image showing the material that failed and the reservoir that was impacted. It actually made a wave that overtopped a dam here. The dam didn't fail, but it caused a huge wave that came down and impacted a bunch of cities below the dam. Here's another image of the material that's filled across the reservoir that's, of course, now sitting there today. A couple of these other examples, you'll look at this Portuguese Bend example in lab where we have some issues with water here, and you know, some of it is due to no city water and having water wells and things like that that might have impacted how much water was seeping into the soil here. And there was some structural issues there, the geology side of that. So when you get into lab, you'll kind of look at what happened here and try to figure out who might be at fault here, whether it was the homes that were built there or the city. And then finally, the last one we'll talk about for a trigger was volcanic eruption. So we did mention that. We talked about mud flows, but this happens numerous times when there's big volcanic eruptions. One, because it's a large shock event, of course, and there's material, but a lot of times eruptions cause melting of snow or glaciers that sit on top of the mountains. And of course, that's a water source that mixes with debris, and then we get debris and mud flows that move down slope. And of course, volcanoes are already steep slope, so a lot of factors kind of line up. So a big trigger is these eruptions like that. And I know we mentioned this briefly, but when we looked at volcanoes, talked about lahars, this Nevada del Ruiz was a prime example of how a small eruption created a huge mud flow because there was a glacier sitting up on the volcano, and it melted and it moved down slope, mixed with all the material, and even though the town was relatively far away, 15-20 miles away, it was still impacted by a large mud flow. And so things like this can be potentially avoided by creating these hazard maps we talk about, and you know, letting people know that there is a high risk there. And although that was attempted in this area, it was not done very well. So that's kind of the overview of all of our mass wasting landslide stuff. So you want to be able to remember the factors that are controlling slope stability, understand how they affect slope stability. We want to know about how to label different events by looking at the material and the movement. We want to look at how to mitigate some of these problems. How do we make slopes more stable? And then you want to remember the triggering events that are also playing a role into whether there'll be a mass wasting event or not. And as always, if you have any questions or you are confused about some of the content in the PowerPoint, please don't hesitate to contact me.